we were here yesterday, so we were saying, what's an image? Okay, so we have an image. This image. Okay. Let's make it non-square image. So we have 0, 1, 3, 0, 1, 3, 4, the origin. Origin is 0, 0 point. It can be anywhere. So if it is put in the upper left corner, but it can be anywhere. Yeah, so and then our image, so we have to define two axes. So let's say this is the y-axis, this is the x-axis. Another way to call it is r-axis for rows, c-axis for the columns. And then we say an image is a function of some domain. Our domains are some domain into some range, and our range is a vector. And then, for instance, let's say that we have a color image defined like this. Okay, so let's try to be more formal here. So we say an image is a function, and because we will have a color image, this will be a vector. We will see. So it goes. Now it is a non-square, so you have to define the two spaces. So you will say image of y, x. You have to specify which is the order of the arguments. So it is a function from y. Y goes from 0, 1, 1 r goes. It is a discrete set. So if it is a discrete set, we use brackets for that. Times, and then this is y. Right. And then we have x. X goes with the 0, 1, 3 minus 1, x. And we have to go into colors. Okay, so let's go to the colors. This should be blue, okay, because it's our domain. And now we go colors. Let's say that our colors are three numbers between 0 and 255. So we have 0. X, 0, 1, 255, and we have three of these numbers. So because of these three, this is a vector. Okay. If we don't have, if the domain is just a scalar, then this is a scalar function. So it is not a vector. So in our case, so in our cases, we can also write this function as also write. So let's say that this is yx. This is yeah, let's colors. Colors. So let's see those colors. This is giving
With respect of days, I got.
okay. This function here. This function here, the domain is a vector. Okay, so it is a vector. It is positive this one here. We have a single number, just one number. Then it's a scalar. Scalar function is just one number. Okay. So this is the range, this is the domain. Very often we are not very careful whether we are writing YX or XY, or also I telegraph. Well, very often I also write it like this, Y R. In the slides, it is written like this. The slides Y P. And these are vectors because they are made full components. And typically, we are not very careful about YX or XY. When you are implementing things, you have to be careful. But when you write, you prefer to write in this way. But you have to, you implement especially, you have to be clear where the origin is. When you say 1, 3, is it? So if I say the image at 1, 3, what are you referring to? Are you referring to this picture or are you referring to this picture? And so this has to be clear when you implement the things. In reality, so in our course, we will not go to such small details. But when you implement things, you have to be careful about those. So an image is a function, and another thing that this is a function, and another way to specify functions is by a set. So you have to give a set. So an image is a set of locations, and the image at those locations. So if you want to put colors, this is red because it is in the output domain, and this is blue because it is in the input domain. And it is this set, a set of locations and values of those. Actually, if you think of any function, this is just that. So if you think of, I don't know, the function y equal x squared. This actually this is a set. So this function, as I said, where you have the points 0, and you have 1, or have all the points in between. It's an infinite length. I haven't written the ones I know by heart, but you have all the points in between, absolutely all. But when you draw this set, it's the curve there. So actually, an image, so every function is just the set. Okay, what is the input? What is the output? It's going to be absolutely correct. As I did here, and this is a scalar function. The output is just a scalar. Okay, good. Any questions so far? No? Okay, so this is what this is saying, that an image is just a collection of locations and values at those locations. You can see that we have here bold letters. So bold letters means vectors. Okay, so location is a vector, so it is bold. The image here in this particular case is just a scalar, but they have represented that a vector. So this is inconsistent. This is line. This is consistent. But you get it. Okay, so yeah, so at every point you have the red, green, and blue values that are just green numbers. Typically they are between 0 and 55. And then we have this image formation model like from yesterday. So you have a real life object, you have an image device, and then you record the projected by this device. And you need an energy source. The energy source in real life and in photons from the sun. But you can do it in a microscope, you have to electrons. Neutrons, X-ray photons, whatever. And the imaging device will transform the input image. So, because actually this is interesting. This is 3D. This object exists in 3D, but this image only exists in 2 dimensions. So somehow I have to collapse all this information, this 3-dimensional information, to a 2-dimensional plane. And for instance, the real life, what we see is just the surface of that object. That is the reduction. When you are doing an X-ray image, it is the sum of the integral or the on the path of the object. So this is radiography of the pure object. So, but you have to earn something that is 2D, something that is 2D. And then you have to record that image. Recording involves a camera. And this camera, now most of them are digital, but it can be whatever kind of recording device. And then you have to quantize the space, something step. And then you have also to discretize the intensity values, because you cannot represent in a computer, you cannot represent the whole continuum of values in the real time. Okay, so the process is like this. So it happened to the image. This to the image is a projection of how you have to convert the 3D object into 2D, and the conversion depends on the energy source. So X-rays, why X-rays give you information of the whole object, while light, does not. Is it change? Both have problems, but the difference between X-rays and light. Why can you see inside? So from the physics point of view, what's the difference between X-rays and light? The wavelength. Because the wavelength, and wavelength and frequency is one. And the energy of the photon. Let's see, also the frequency. So the energy of the photon. Okay, so the difference is in the energy. And then X-rays have a lot of much more energy than light. And that means that they travel more speed. Would you say that? So X-ray photons have more energy than light photons. So they travel quickly. That expect this stage. They both travel at the speed of light. Both. Okay, so it is not the difference is not in the speed, it's in the momentum. Okay. So it is in the momentum that so one has more energy than the others. So there is a photon coming in, but one is has less energy than the other. So somehow this less energy allows it to interact, or it has a larger wavelength. Somehow sees more feels more the presence of more atoms. So it feels the atoms around. They interact with the atoms, and photon interacts with the atoms, and they cannot go through because it is interacting with the matter. But the wavelength of the X-ray photons is much smaller, so it doesn't see the atoms. For the photon, the atoms are much more separated. They have the same separation, but in terms of wavelength, they are much farther. So they don't see the atoms so well. They traverse without interacting with the atom. So they can traverse without seeing any atom. In fact, that is why it's true. Okay, so this is about this real image. So the real image is made by somehow that collapsing 3D information into 2D information. Good. But we want to put it in a computer. In a computer, we have discretized spaces. One is space, the other one is density. So here we have discretized in the space, but not in intensity. Here we have discretized in intensity, but not in the space. And in the computer, we have to do both. And this is exaggerated, so that we can see the big effect. But the same kind of effect is happening when you acquire digital image. Okay, so how do I quantize up a space? So space quantization is called sampling. So this sampling, we will refer to this continuous image that is defined for all points in space. We will define, we will call it IC, I continuous, image continuous. And we will use two variables, variables, space variations that will be rho and chi, rho for rho, chi for column. And in the computer, we will have the distance thing. In our notation, these are square brackets. Okay, so parentheses is only for continuous functions. So the argument is continuous. Here the argument is discrete. So we will have the row and column that is discrete. So it is, you have this continuous image. You have a grid on top of it. This grid is defined by separation delta. Then we have to convert somehow. We have to keep for every square, for every little square, these are our pixels. We need to keep a single value. And one possibility to do that mathematically representing that process. Okay, I will compute the average of all the values in the square. So what is the average of all the values here? See, what is the value, the average of all these points here? This red. What is the average here? Is yellow. Yellow, red are numbers. Okay. So I have to compute the average. And computing the average of a continuous function is computing the integral from within the area of the square. So actually, if you look at this, if the origin is here, just in the border, this point here is R delta, and the next point in the grid is R. This is R plus 1 times delta. Okay, so I have to integrate. I have to integrate from R delta to R plus 1 delta. And the same for the columns. Okay, I'm integrating this function. So integrating is summing, and then I have to divide by the area of that square. And the area of that square is 1 over delta square. Okay, so this is just abbreviating. Okay, so we have a continuous image. Yeah. 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 So you take all the continuous values within one pixel and you compute the average. And this will be your sample image. Okay, so here is that process. So here you are computing the average of all these pixels. This one, the average of all these pixels. This one, it is a little bit red, but it's almost white. It's big. So, okay. Yeah, the difference. Okay, now we have to quantize colors. Quantize colors, it is the same. So I cannot represent this average, can be whatever number. So it can be any number in the real line. Any. We can have infinitely many digits. So I cannot represent that in the computer. So I have to quantize the intensity tool. And the quantization of the intensity is represented here. So I have a continuous, so the average is continuous, but I cannot represent that continuous. I will discretize the small steps, and then these are the steps. So all these values be substituted by this one. All these values will be substituted by this one. Actually, this is a function again. So we have what is the input, what is the output, and you are giving for every point in the input, what is the value in the output. So we quantize, we can represent that process basically. So we can say, okay, there is a continuous function is a vector. This is continuous, and we have colors. Good. Then it goes to sampling. I don't know how to call that. I would call it I in it's another vector because it has continued. What of this? Now the space is quantized. Actually, let's say we use R cube. Okay, that's the say better because it's a better notation. Okay, that's what you say. Say n. Okay, so now I have discretized space. I have discretized the space in such a way that R responding to n is n times n. So the location of a pixel n is n times delta. That is the continuous location. Okay, so we are doing something, and then so this is something in the space. Now we are quantizing. Quantizing is in intensity. Intensity now. So intensity now is also basically here. Our sample intensity. So sample is in this and it's a vector. This tilde here is just to say this is a different function. This is the one with the averages, but this. So this image here, this image here, before. So this image here is fully defined everywhere. Everywhere you have a value. This image here, you only have values at the location same. Okay, it should be in a very fast way. So you only at the location same is defined. But the values can be whatever. And this one here is also defined only these points. And the intensities are also discretized. Okay. Okay, good. So, yeah, this is actually this is interesting. We don't care much about MATLAB, but this concept is interesting. Okay, so MATLAB has command to read images. So you say read this image that is of this form. Okay, and now what is the class of I? So the class of I is 0.8. So U means unsigned integers of 8 bits. So unsigned integers of 8 bits, they go from 0 to 5. What is the size of I? So the size of I is 600, 1200 split. So that is, this is the height, this is the width, and this is the depth. This is called depth. And it is how many channels you have. And we have 3 because we have the RGB channel. Okay, now I show that image and I get this one. Okay, and there are a few things that we recognize here. So you have to separate the image content from the image display. So one thing is the functions, and the other one is how you draw the function. So these spaces are somehow compressed. Why? Because this length is 600. This is twice that. But the image, but the ratio between these two lengths, so in reality is 2, but in my display it's not 2, it's smaller than 2. So I have compressed, so you have to separate the image content from the image display. Something is what the function is, and the other thing is how you draw the function. And now you make it with true ratio, scale ratio. Now this length is twice this one. Okay. And this is called matter, this is called true size. So this is an important process that you have to separate the image content from the image display. Okay, so far so good. This is somehow what we expect. Okay, now where is the origin? The origin for MATLAB is here. Okay, and it is the 1, 1 point. But you see, this axis goes from 1 to 1200. This axis goes from 1 to 600. So the origin is there. Okay, so now let's say that I draw the region in that image. Okay, so now you have a sub-region of that. And now the origin has changed. So you can deal with this in 2 ways. So either, yeah. So now let's say here. So you have a big image. So that you have a big image like this one. You have a small one. Have a small one, that is this one. This one. And the origin, the blue origin. Blue origin. So this is actually the 0, 0, that is same thing. 1, 1. 1, 1 is for that. This is better. And now this is, so this point here can say 2 things. One is this is a point 100. This point is this one, and then this point here we are traversing. This is y, this is x. This point here will be 100, 300. Okay. But my origin, my upper left corner is this one. Or you can say, no, this is now a new image for me. This is now a different form now. This is for me a new image. And in my new image, it's the 6 form. This is my 6 form. So it is very important. Actually, it is nothing more than changing the list of location. We are saying. So what you are doing with these locations? Are you resetting it to 0, or you are keeping the old origin? You can go to both things, and both things make sense depending on what is your preference. So, for instance, here, yeah. So here, you can see the origin is not 0, but can move it and make the origin. You see, both things make sense, but you have to keep track of what you're doing. Okay, so okay, maybe yeah. Okay, so now we know the trick. So let's load another image and display. Okay, so now we have before it was a JPEG image, now it will be a GIF image. We read the GIF image that is in format GIF, we show it, and this is what we get. So actually, when you look into the the size of the image. The size of it, you have the height, you have the width, but you have no depth. Okay, and so it looks very strange, isn't it? And when we read it, we read something else that is called the color map. Okay, so what the color map is? When you apply the color map, you get the right, the right colors. Okay, so what is the color map? So we have said we have an image, and for every location, in this location here, we have a vectors. And for every location, we have a vector. 50, 20, 100, and 75. Right? And you have the same for every pixel. But what you can do is, okay, so what if this pixel has the same color as this one? They have exactly the same color. They also have this vector. So I can do something else. That is, I can construct the table. Construct the table. And in this table, I write there my colors. 50, 100, 5. And I can say, okay, this is index 0. Then index 1 will be another color. 0 and 5, another. And this picture. So now you write your image. This is using index 0. This is using index 0. This is using index 1. So, okay, so now the image itself, you are not keeping the colors, but you are keeping the indexes of those colors. And why do you think this could be used? For
Be more into school memory.
yeah, to be more efficient in memory. Okay, so let's think a bit of what is the size of what are the sizes of these things. So let's say that we have, let's put an image. This is size n, n of x and y. So I always try to be consistent. It's outline. Okay, so how many numbers do we have? Vectors n, y, and x, and then times 3, because I have to store for every point that have to store numbers, and these numbers they occupy a single byte. So this is bytes. Okay, now I'm doing this trick of keeping just the numbers. Okay, so now I only have to keep one number for every. So this is 3 times as small. That is a 3. You have to keep the table. Okay, let's see, because it's the size of this table. So let's say that my table is it has 256 colors. So it has 256 colors. I have to keep the table. But this is the size of it. We put numbers. This is no, it is 5. Okay, 5. Okay. So this is 25 millions. This is very small number. So you are much more efficient in space. But now you are constrained to use only 256 photos. Actually, your table can be as long as you like, but typical sizes is only 256 photos. Okay, so for representing this kind of drawings, these drawings will use so many different colors. 56 colors, that's fine. For representing real life image, represent real life image with this one is minimum 14. But this kind of a story, the vector is called the true color image. this one is called a color map. Okay, good. Color map. This is color map versus color map. So the difference is in one of them you are constructing a table and then only keeping the indexes with that input. And in the other one you are keeping the full vector. Here is another interesting concept. That is, we have said the colors typically they are between 0 and 5, and you are not constrained. So all you need is that is a vector. So let's say that I have this image that goes when I'm lazy, I don't want to write from 0 to r minus 1 and times 0 c minus 1 and so on. You just say, okay, this is this tree. This is the integer set. So this is this tree, and you are going basically. So here you go to 0 to 5. Okay, what if I construct a new image? I construct an image that would be I divided by 2, 5. This will go from set square to now 0, 1 over 2, 5, 2 over 2, 5, all the way to actually I will divide by 256. Doesn't matter, you can divide by 8. That's one. Okay, so now it goes from 0 to 1 in steps, delta in intensity, 1 over 2. So now you see the quantization. So, and this image is the same as this one. Exactly, it has exactly the same information. Exactly the same. So it is not a requirement that it goes from 0 to 55 steps of 1 and go from whatever to whatever in steps. Okay. So you can also do that. Actually, the color tables, the activity is stored in this this convention of dividing by 5. Of the color map is a table with fractions. But the fractions should be understood. That is the red channel context. This is more red than this one. And the maximum red is 1, the minimum red is 0. In whatever your scale is. So for this scale, it's 0 to 1. In this scale, it was in the previous scale, it was 0 to 5. So time to make a break. Okay, so any question up to here? Okay, so let's continue here. We have a couple of examples. So it is the same image, but it is encoded in 2 different ways. One is through colors, so these are just the vectors, the RGB vectors. Here is a color map. A color map, index, the table has 8 bits. Okay. So this is how many entries you have in the table, and this is how many bits are so in the output. Actually, a table is nothing more than a function. This is another way of writing a function. So this one has 24 bits. We know why, because it has 3 times 8 bits, 8 bits for each one of the colors. And this one is 8. So this 8 is patience that I have used. 8 bits for the index, 24 bits for the output. Okay, good. From the distance, I'm sure that you cannot see almost any difference. If you get really close, you start to see a difference here in this bright spot. You see that this one doesn't have as such a high quality as this one. This one is quite high. You are limited here to 256 different colors, very much restricted. But if you look from the distance, you cannot see this difference. So it depends on what is your purpose. You don't need to keep so many different values. So here let's put easy numbers. So let's say that this is 1,000 pixels, 1,000 rows, 1,000 columns. So this has 1,000,000 points. And if you want to keep every vector, you need to keep 3 million numbers. Here, you only need to keep 1 million numbers. So it is 3 times more efficient, but you have to sacrifice something. Okay. Yeah, it's a zoom of how this thing here is quantized. So you see that there are funny factors. Okay, so this is MATLAB factor. The concept we already have it. Yeah, this one is interesting. So now you can construct color maps of any let's say color maps of your interest. Okay, so let's say that we construct that one. So a ramp is just because you see it goes from 0 to 255 divided by 255. So it is the same scale that I wrote before. So it is this one goes from 0 to 1 in steps of 1 divided by 255. Okay, that is our graph. And now I can construct different color maps. I can construct a gray color map, will be called K color map, K for black. So it will be, I told you yesterday, gray images. If you put the same number in the red, green, and blue channels, you will get the gray. So you put the same graph in the 3 channels. Now we construct the red color map. The red color map will have the one in red, and then the other 2 channels will be set to 0. And then the green color map. So we will have 0, the red, and 0. For the blue color maps, we will have 0, 0, and then the red. And now we can represent any image with any one of these color maps. So for instance, we can read this image. This is 2 color. And now I can take the channel 1. Channel 1 is the red color. And so I'm just looking at the R component of the RGB. Just taking it. And I'm representing it with the gray color, map. And I'm taking now the green channel with the black color, with the gray color map, and the blue channel with the gray color map. So I have indexes here, and I have here 2 values from 0 to 255, and I'm using those values as if they were the indexes in my color map. You see that? So I can use the gray color map. I can use other color maps. I can use other color maps. So I can use the red color map. So I can take these values and use them as indexes in the red color map. I can take these values and use them as indexes in the green color maps, so on. Now because my color map is, for instance, this one, it is 0, the ground, 0. All these would be different levels of green. And they will go from black, that is the 0, 0, 0, to the fully green, I don't know, which is the greenest pixel. This one, I don't know. This one, that is the 0 to 55, 0. I have all the values. See? And the same for the blue. And this image here is the sum of the string. You take this string collapse them into single collapse them as you put them and you superpose them in space, and you have somehow a device that emits red light, and then another device that emits green light and blue light, but they are all in the same location in space. Then what you see from the distance is this thing. And actually, this is the technology to display. You decompose into 3 channels. You display the 3 channels independently, but they are superposed. Then you are receiving photons of different wavelengths, and each one. So this is red, blue. This is all the time the same. This guy likes a lot to reinforce the information once and again. For example, this one is interesting. Let's look at these grapes here. The grapes are mostly blue, so I should have a lot of intensity from the blue channel, and I shouldn't have so much from the red channel. The red is much darker than the blue channel in this direction. Why? Because this is almost blue. So I should see a lot of blue intensity and less of red intensity. No zero red. So this is not pure blue. This is not blue as crystal. This is pure blue. Okay. But so it is not pure blue. So I need some red and green light to reproduce this color. But the same concept applies to everywhere. So this leaf here, this leaf is red and green. So the outer part of the leaf is very bright. The inner part is very dark. Here it is the opposite. The outer part is dark, but the inner part is bright. Because I need a lot of green here to reproduce these lines. And I don't need green to reproduce the outer part of the leaf.
Answer, right?
Yeah, so the more red you need, the higher the intensity of that channel. Yeah, and then we separated before, we separated the image content from the image display. You have also to separate it from the image storage. So when you want to store an image, there are different file formats. So you can say that all the numbers, thanks to that. That is not very efficient, and that is why we have different file formats. We have bitmaps, we have JPEG, we have git files, and those are. We will see that at the end. The last lecture is about this thing, but it is how you store in an efficient way this array of numbers. A full array of 3 million numbers. How you store them, and how you store them without occupying too much space and without losing. That will be many things. What if images are vectors? So let's say I have image 1. Have image 1 is a vector. So it is 1 is kind of vectors. What we have image 2 is another vector, and I construct a new image. It is 1. Actually, if you want to be pure, you need to be arguments. What we are saying is, I'm constructing a new image that at every location, it is the sum of these 2 vectors. Let's say that these 2 vectors are of this kind. Okay, so they have some locations, and then the colors go from 0 to 55. Or this one, does it go from 0 to 55? Because you can be unlucky. You can be adding 255 values, and then you have 510. So these functions does not belong to this space. You think of all the space of all images, that this is the domain, this is the range. This I3 does not belong to this space. Doesn't matter. For us, an image is something that has a domain and has a range, but the range of I3 is different from this range. If you want to make it the same, you have to pick the average. And information doesn't change. But now this one, you will have to approximate because this one is this big. If you divide, I don't know, 109 divided by 2, it is not any of these numbers. Okay, but you have to round or whatever. But apart from that, now it belongs to that space. Okay, so I can do that. I can take, yeah.
Some two images is clear. And you said that there's no further reasons it's better than the specification of the why do we with the others?
If you want to make it fit in the 0 to 55, you know, if you don't want to make it fit, then half of the. Okay, so I have this image, I have this one, I want to add them. And the addition of the two will be something like this, okay? And before you add, you have to adapt this, the locations. So the locations for this image, has locations that this one doesn't have. So all these borders here, all these borders here, they don't exist here. So you have to make only the addition where it makes sense. Okay, so you will have to drop the one of them for adding. So that means you have to make if this is a set of R1 locations and I1, and this is a set of R2 locations, right? Before adding, you have to restrict your sum only to those locations where these two are the same. So if you call omega 1 to all these locations, and omega 2, let's say, of all these locations, then this sum is only defined at the intersection. So we are dealing with functions. They are very nice functions, because you see they're functions. And we have to make the two ranges consistent before adding. Otherwise, one of the two will not be defined. This region, this function is not defined. So you can only make the addition where the two functions are defined. Then this is the code to do that. So you see that this part here is to make this restriction to crop this one the size of it. Just to take the count back. If you are interested in MATLAB, and you can analyze this line. But this line is the one that is making this equivalence. Okay, so what if we are multiplying? And multiply, so this. So this operation was here. So this operation is clear. So I have to be careful with the domain, but otherwise the range is well defined. This is a 3D vector. This is a 3D vector. The addition of two 3D vectors is well defined. What is one? Let's say that I construct a new image. Yeah. Okay, so I construct a new image. That is a multiplication. Are you happy with that? Are you sure that? No, I don't. You need homology. Correct. Can you multiply two vectors? No. No. So the standard multiplication of vectors is not defined. This operation doesn't exist. You can compute the inner product. The inner product is not defined. Something else is if it makes sense or not. That is something else. But this is well defined. And this is also well defined. I can compute the outer product. Cross product. So this is inner product. Inner. Of the outer. Cross product. This is inner product. The inner product is the vectors you. It takes two vectors and returns one. Scalar. You take two vectors, have a scalar, and the outer product is two vectors. Takes two vectors. Does it return? Does it return? Another vector. But this one doesn't exist. Doesn't exist. So you could say, no, what I mean by that operators, I will define the dot operator. This will take two vectors and then another vector. But it will do it in this way. It will take, it will return u v times v in so square. Sure, you could define it in but it's the one that makes no sense. U v v then u v v and u v. This is my operator. And now it is defined. You have defined this one. It is also defined. It is not the standard, it's the point-wise. This first, second, third, but it is not the standard. That's another name. Yeah. And has the name of the guy. Okay. So you have to specify what operation you are doing. If your operation is a standard, that's fine. If your operation is not a standard, you have to define what the operation is. Okay, so now we want to multiply this component by component, this is multiplication. And then multiplication. Okay. Yeah. Here. Here. This is the point was multiplication. Okay, another interesting operation. So let's say that I have this image, and it has red, green, blue channels. And for every channel, you can measure what is the minimum and maximum of each one of the channels. Okay, in terms of notation, this is not purely correct. If you are given a set of values, set of scalar values, can you compute the minimum? Can. If the smallest one is the minimum of set of scalar values. If you take a set of vector values, it's the minimum. It's not defined. The minimum of a set of vectors doesn't exist. The concept doesn't exist. Okay. So to be correct, this cannot be a vector. This has to be a scalar. Pay very much attention just for you to learn. This is very important. But when you are doing the exam, you make all the time this kind of mistakes. You compute minimum of vectors. You compute things that do not exist. And you have to be, as engineers, you have to be correct about the language you speak. Okay, so if you are speaking mathematics now, you have to speak correct mathematics. It's not speaking English like the way you like. It has a grammar. You have to follow that in English, the same in mathematics. Okay, so this is not absolutely correct. So this one is applied to each one of the channels independently, but we get that. So this is the minimum of the red channel, the minimum of the green channel, and the minimum of the blue channel, the same for the maximum. And for each one of the channels, you do this operation. So let's try it. So for each one of the channels, so now there are no vectors. I'm doing this operation at the level of channel. I take one of the channels, whatever that is, and I subtract the minimum of that channel, divide by this, multiply by 2, this will be the new channel value. So I do this at every location. Every location, I do that. And is this operation well defined? This is a scalar, this is another scalar, the subtraction of scalars is well defined. The division by another scalar is well defined, so it's the value operator. Okay, so I will take the 3 channels, apply this operation, and substitute and construct a new image with these new images. So, for instance, if you want to express that, what is the grammar to say that? So you can say, okay, this is my transformation on the image I. And this transformation is that at every point I'm doing this transformation. The transformation is defined in this way. So now my new image is a vector will be the red channel, okay, green channel, and the blue channel. This is the correct grammar to say that. And if you want to be even more precise, this is the minimum of the input image. This is the maximum of the input image. We can be even more general. So I will substitute this by that part here. So this particular form that is in the slide is the particular case when MJ is equal to 0. This is 5. Okay, so the general transformation is this one. Most general transformation we have. Right, that is Fj plus and I. But it is not necessary to write. So when the argument of I is understood, then we don't need to write. So only if there is ambiguity, you have to write. Okay, so this is the most general transformation. What is this doing? This is taking. Okay, so now it's a function. J function y. What kind of function it is? It's a drawing of J of y. It's the shape of that function. It's a number, this is a number, and this is your argument, and then this is a number and another number. That is of this form. Yeah, so A plus that. You agree? That is the shape of it. That is a line. So it is a simple linear transformation between I and J. Which transformation? So I, we have two values, the minimum and the maximum. Now J, we have other two values. This is the line. So let's look at this. So let's say that I, the input image, takes the minimum value. It takes the minimum value. This is minimum minus minimum. So this is 0. And then 0 multiplied by anything is 0 plus J. So this point here. What about the maximum? It is the maximum. This is maximum. Maximum minus minimum divided by maximum minus minimum. So this is 1. And if this is 1, now this function to be clear. And then we have the maximum value. It's this line. So it is a transformation that takes the minimum and the maximum of the image and transforms it into a minimum, so takes the minimum and maximum at the input and transforms it into a minimum and maximum in the output. Only that, in this particular case, my minimum and maximum in the output, they were 0, 5. So this transformation is really, really important. It is called contrast change, contrast attachment. It is affecting the contrast. Contrast, actually, when you talk of contrast in an image, is the difference between the minimum and maximum. So let's say that you have an image whose minimum value and the maximum value, they are very close. It's almost the same gray value all the time. So you don't see differences. Let's say that you have an image that the minimum and maximum are very far away. Now there is a lot of contrast. Okay, so this is the contrast enhancement. So you say each one of the channels, you apply the transformation of each one of the channels, and this is what we get. Here you have fewer contrast, like a smaller contrast than here. So here, the separation between dark and white and bright values is larger than here. And you could do the opposite. You could collapse the minimum and maximum towards very similar values. And then this would become kind of gray. Have I changed my image? Let's get that. So, for instance, let's say that you take this image, you apply this contrast stretching or change or whatever you call it, uh, and then you compute what is the difference between your original and your transform image, and you don't care if the difference is positive or negative until the absolute value. Okay. You do the same, but now the image is not so the difference is not just the difference, it is the logarithm of the difference. How you show. Okay. So what we are doing is I is the image, J is the quality zero JPEG. We saw in the end of the day. The quality zero JPEG is the one that occupies the smallest amount. And if you compute the difference between the two, you don't see much. But now I compute the logarithm of the difference. I display the logarithm of the difference. I rescale it. This is this operation that we showed before. This is the transformation that we saw before. Now I rescale it. I see more. If I represent d squared as something different, so the d is all the time the same. It's all the time the same. This is this difference with the two. But depending on how you display, so what is the transformation that you apply? You will see different. So you will highlight more or less differences. Yeah, so it has the
We're going to introduce the numbers of maximum aluminum.
they will be taken from them. It will be the minimum and maximum of image file. You give me an image, I compute the minimum and maximum, and then I apply this transformation.
So the formula we get there in the colors change. Not always functioning in the single one action.
No, actually, if you want to be correct about the notation, here you should have introduced NK and for the minimum and maximum that you want. These are parameters of your transformation. So you have to say this one. And in this particular case, we say 0 and 2. So it's
For every
at every pixel, so for every input pixel, you are applying this transformation. Okay, so the information is the same. It's just the, but depending on the way you transform it, you see it differently. And you see differences, for instance, just the linear transformation. So just applied to D. We just see a very bright point here every time. Otherwise, it looks like, okay, you did a very good job approximating this image. This is not true. When you compute the logarithm, and you see that there are differences everywhere. If you see in this way, now you see some differences, but not others, and so on. So depends on how you treat the information and see something or not. Be able to recognize some pattern. Okay. Yeah, this is something of Magda. So that's fine. Funny pattern. Any question? Okay, so otherwise we move on to the next slide. what is a histogram? So the histogram is a count of how many times you have seen the black color. Give an example. So let's say that we are given this image. Let's say that this image is defined between 0 and 5. And now you count how many times I have seen the value 0. Count. How many times I have seen the value 1, the value 2, the value 3. So you make a plot of how many times you have seen each one of the values. In this particular image, we have seen the value 10 about 3 million times, and the value 255 very few times. It's not so. 255 would be this star here. This 10 be the black sky, the background. Okay, so we see as complete. What about this image? With this image, you do the same. You count how often you have seen each one of the intensity values. And this is now your histogram. Now in your histogram, you recognize two modes. So one lobe here, another lobe here. So do you know which one is which? What is this? Just that part. Yeah. So it is the sky. Sky that is here white. So it is this one. What about this one? It is the rest. Okay, even in the rest, we see two lobes. Which one is those? One is the ground, the other one is the tree. One is darker than the other. I would say the tree is darker than the ground. This part of the tree is very dark. This part of the tree. Okay, more. So we can have now this image, and we can recognize the same kind of pattern. So now this bright thing is the snow on the sky. There's this one here actually are areas, and then this is the one between and so on. Now, color images. So counting is only defined for each one of the channels independently. So now we can, if we are given a color image, now we have 3 histograms. We don't have just one, but you have a histogram for red, a histogram for green, and for blue. And we may even try to understand this histogram. So listen, let's look at the blue histogram. So in the blue histogram, a region that is pretty dark, a region that is pretty bright. So the bright region is the sky, the dark region is the rest. For me to send in this part, I don't need the blue. I will need a little bit of blue one. And the red is the opposite. So almost everything looks red, and there will be all kind of reds. This is much more uniform. And even this spike here, the spike is there are some points that are saturated. So the camera wanted to record more photos from red, but it is saturated at 55, and the previous at 55. Have you seen analog to digital converter? So there is a voltage, and this voltage is translated into an analog. So the voltage is saturated with the mass of the capacity. That is why these are saturated. Say here. Say here. Nothing new. Okay, so now a histogram. A histogram is another function. Another function whose domain is 0 to 55. These are intensities. And whose range is could be from 0 to the total number of pixels. The total number of pixels is the multiplication of number of rows, number of columns. Okay, so it is a function, and it is a function that is defined in this way. So for every monochrome image G, and E here should not be mode. Mode is for vectors. So for a monochrome image G, the histogram of G will take an argument that is the gray value you're interested in. Then you count how many locations this image G takes this value. This is counting. It's the cardinal operator. So it's cardinal of this set. This set is made of all the locations such that G at that location of size. A more correct way of writing that would be of a histogram of an image G at a particular gray level G, small g. So this is the cardinal operator. Cardinal is applied to a set. It's an operator that applies to a set. Set of all those locations such that the image of that location is related. So this is a well-defined set. This is the cardinal of that set. And it is all the time same thing. And recently we have image. And now this is interesting. So these images are represented with 4 bits. So 4 bits means that the gray value can only take values between 4 bits. So G is a function. I don't care now about the I'm caring about the output. So the output is 4 bits. It is 4 bits. I'm going to take value 0, 1, it's a maximum. 15. 15 is 2 to the 4 range. Here you got 4 bits. Actually, when you extend it with 8 bits, this value, this is 5. So there is no magic. 5. It's only the maximum number that you can represent with 8 bits. This is the maximum number that you can represent with bits. Okay, so now I can construct images. These, okay, I will say to black if the value, if the input pixel takes value 0, and otherwise I will set it to 1. So I will construct this operator. I will construct this operator. We'll construct an operator such that some location, so it will transform into right. But the way that and it receives an input value rate G E I is equal to J 0 1 I is equal to this is my new operator. And this is that operator applied to this equal 0 equal 1. Which are the brightest points? The brightest points are these ones. So that's the darkest points, the legs. And then you have all values in between. Then you count how many zeros you have here. I have 29 zeros. How many zeros you have here? 24, 54. How many zeros we have here? So, and this is your histogram. So counting, this histogram counting, see here, you can decompose this image into different layers, each one for each one of the gray values. Then you simply count how many active pixels you have in each one of the layers. Any other question? Okay, so otherwise we stop here.